Hi, I'm Tsao. I'm going to present the second part of this tutorial entitled Intelligibility Evaluation and Speech Enhancement based on Deep Learning. First, let me briefly introduce myself. My name is Tsao. I received my PhD degree under supervision of Professor Jinghui Li from Georgia Tech. Then I worked in NICT, Japan for 2.5 years. Currently, I'm a research fellow, professor, and deputy director in the Research Center for Information Technology Innovation. My research interests include assistive speech communication technologies, audio coding, deep neural networks, biomedical signal processing, and speech signal processing. In this part, I will first present the speech enhancement architecture. Then I will present 6 factors that should be considered when designing the speech enhancement system. After that, I will show some applications of speech enhancement on assistive voice communication technologies. Finally, I will summarize this part of the tutorial with concluding remarks. First, I will introduce the system architecture of deep learning-based speech enhancement. The deep learning-based speech enhancement is a regression task and has 2 phases. In the training phase, we prepare paired noisy and clean speech data. Both noisy and clean speech data are first converted to spatial features by applying short-time Fourier transform. The speech enhancement model transforms the noisy spatial features and generates the output. Then we compare the difference of these outputs and clean spatial features. Usually, we can use L1 norm or L2 norm, that is MAC or SXDR, to measure the difference. Based on the difference, we then update the parameters of speech enhancement model. In the testing phase, the noisy speech waveforms are first converted to spatial features. Then the trained speech enhancement model transforms the noisy spatial features to generate the enhanced one. By a waveform reconstruction process, we can then obtain the enhanced speech waveform. This work was proposed in 2013. If we look at the overall system now, the system is very simple, but actually this is the first work that applies deep learning for speech enhancement. Here are some demos. These are spectral plots. For each plot, the horizontal axis shows time. The vertical axis shows frequency. The color denotes the energy. A lighter color denotes higher energy. This one is a noisy speech. This one is an enhanced speech processed by a traditional speech enhancement method, MMSE. This one is an enhanced speech processed by another traditional speech enhancement method, KLT. This one is the deep learning results. Let me play these samples. From left to right is original noisy, MMSE, KLT, and DDAE.
他不小心把茶杯碰翻了。他不小心把茶杯碰翻了。他不小心把茶杯碰翻了。他不小心把茶杯碰翻了。
As can be heard, both speech quality and the intelligibility of deep learning-based results are much better than traditional method. We can also see from the spectrograms that the spectrograms of deep learning-based results show more clear speech structures with less noise components as compared to the other 2 traditional speech enhancement methods. This photo was taken from a street in Taipei. Motorcycle is a very common commuting tool in Taiwan. When riding a motorcycle, however, we cannot use normal air conductive microphone because the wind noise will interfere with the speech. To avoid the wind noise, we can use a bone conductive microphone. The idea of bone conductive microphone is to capture the vibrations of our skull when speaking. In this way, the wind noise can be avoided. However, the channel characteristics of air conductive microphone and the bone conductive microphones are rather different. We can take a look at the spectrograms. The very right panels shows the speech recorded by an air conductive microphone. The very left panel shows the speech captured by a bone-conducting microphone. Because the bone-conducting microphone only captures vibration, the high-frequency regions are missing, as can be seen from the spectrogram. Let me play these samples. First, the original air-conducting speech. Second, the bone-conducting speech.
他们正往树上喷洒农药。
他们正往树上喷洒农药。
For human, we can still perfectly understand the speech captured by bone-conducting microphone. For ASR, such as Siri or Google ASR, the recognition accuracy are much degraded for the bone-conducting speech. To handle this issue, we propose to use the speech enhancement model to transform the bone-conducting speech to air-conducting speech. Let us listen to the enhanced speech signals. I'm going to play the bone-conducting speech, enhanced speech, and the air-conducting speech.
他们正往树上喷洒农药。
他们正往树上喷洒农药。他们正往树上喷洒农药。
As can be heard, the enhanced speech signals are very similar to the air-conducted speech. We can also see from the spectrograms where the enhanced speech has clear structures in the high-frequency regions. Then the enhanced speech can be sent to ASR for subsequent applications. To build a good deep learning-based speech enhancement system, we should consider the following 6 factors: feature extraction, speech enhancement models, objective functions, auxiliary input, ways to optimize the model architecture for real-world applications, and the ways to increase the speech enhancement model adaptability to new speaker and environments. The last 2 parts are very important to deploy the speech enhancement system in real-world applications. To evaluate the performance of speech enhancement systems, we usually use PESQ for quality measurement, STOI for intelligibility measurement, SSNR segmental signal-to-noise ratio, a signal domain measurement, LSD log spectral distortion, the difference of enhanced and clean speech in the log spectral domain. Since the goal of speech enhancement is to improve speech intelligibility and quality, we usually care more about PESQ and STOI scores when comparing speech enhancement systems. The range of PESQ scores is minus 0.5 to 4.5, and the range of STOI score is 0 to 1. Next, I'm going to present 6 important factors for a speech enhancement system. Let me start with feature types. So far, many different types of features have been investigated for speech enhancement systems. For example, male log power spectrum, log 1P, power spectrum, complex spectrum, and so on and so forth. In this presentation, I'll present some examples of these features. This is a very early speech enhancement system. We have paired noisy and clean speech data. Then we apply short-time Fourier transform to obtain amplitude and phase information. Then we further apply log operation and male filter banks to get F-bank features. We use a neural network model to convert noisy F-bank features to clean F-bank features. Then we use the phase of noisy speech to restore the enhanced speech waveforms. The idea of short-time Fourier transform and male filter banks are based on our hearing system for human perception. This may not be optimal when we use neural network models to perform speech enhancement. Obviously, the phase information is inaccurate. Actually, many studies have shown that phase information may affect the overall speech quality. In 2017, we have proposed to use complex spectral features as the input for the speech enhancement model. We can use the CNN to combine the real and imaginary RI spectrograms to obtain enhanced RI spectrograms. The enhanced RI spectrograms are then converted to enhanced speech waveforms. The motivation of this system is to obtain more accurate phase information. The RI parts can be considered as RGB inputs in image processing. Experimental results show that in terms of the LSD log spectral distance metric, the log power spectral features with DNN achieves the best performance. This result is actually quite reasonable for a speech enhancement model using log power spectral features, and our goal is to minimize the error in the log spectral domain. Of course, we can obtain the best performance in terms of the LSD metric. As mentioned earlier, the speech enhancement aims to improve speech intelligibility and quality. Therefore, we care more about PESQ and STI scores. From the results, we note that RI spectrograms outperform log power spectral features when using DNN as the speech enhancement model. Finally, we also noted that CNN outperforms DNN when using RI spectrograms. This might be due to the good modeling capability of CNN to process multiple inputs. Next, we try to directly enhance speech in the time domain. In 2017, we proposed to use FCN to do the work. The motivation is the same. We want to obtain more accurate face information. We also noted that FCN performs better than fully connected neural networks. From the results, we first noted that FCN achieves the highest STI scores, and DNN achieves the highest PSQ score. The log power spectral features with DNN underperforms these two waveform-based speech enhancement systems. In the previous work, we performed enhancement using frame-based waveforms. Later on, we explored to use the whole utterance as the input, and the output is the enhanced whole utterance. This is our model architecture. The FCN model consists of multiple layers. Each layer has multiple filters. The input waveform is processed by these filters. Finally, a fusion filter combines all the waveforms to generate the enhanced waveform. Because the speech is processed in an utterance level rather than frame-wise level, we now can use other objective functions that require a sequence of frames, such as STI or PESQ. The results showed that the utterance-based input outperforms frame-based input. When we use a different objective function, the utterance-based waveform can gain additional benefits. This is because we can now easily compute the correlation of speech samples between enhanced speech and clean speech. We will discuss the use of STI score as an objective function later. In addition to the input, there are different types of output. Generally, we can divide them into two categories. The first one is direct mapping, which means that the output is spectral features or waveforms. The second one is racial masking. The output of the speech enhancement model is a mask. A point-wise multiplication is carried out to obtain the enhanced speech spectral features. Next, I'm going to present the model types. Many different types of models have been proposed to form speech enhancement systems. For example, DNN, DDAE, RNN, LSTM, CNN, CRN, FCN, and so on and so forth. To further improve the performance, some advanced techniques have been proposed, such as skip connection, highway density connected, attention mechanism, unit architecture. More recently, several ensemble learning methods have been proposed for the speech enhancement task. In the following slides, I'm going to introduce one ensemble learning method. For a speech enhancement system, we generally estimate the speech enhancement model using a training set. The trained speech enhancement model is then used to enhance the testing speech. Because the testing speech may be from a new speaker and unseen noise type, the mismatch between training and the testing may result in poor speech enhancement performance. A previous study reports that there are three major factors that affect the speech enhancement performance notably. They are speaker, noise type, and SNR. We have confirmed the statement by running a principal component analysis. By applying PCA on the noisy training data, the overall training data can be divided into two groups, one for male and the other one for female. If we further apply PCA on noisy speech data provided by male speakers, we can note that there are another two groups, one for high ASMR and the other for low ASMR. The noisy speech provided by female speakers show the same trend. Of course, we can try to prepare speech data from many speakers with a wide variety of noise types and ASMR and train a very gigantic speech enhancement model to potentially cover all testing conditions. However, such approach may not be suitable or feasible for the conditions where computational resources and the data are limited. Instead of training a very big speech enhancement model, we proposed an ensemble learning framework termed DAEME. The model is based on the ensemble learning criteria using conditional overfitting strategy, which aims to train each component model to overfit to or perfectly match a subset of training data. When preparing the DAEME system, we first train multiple speech enhancement models. Then a fusion model is trained by mapping the outputs of these speech enhancement models to generate the final enhancement speech. The system can be considered as a multi-branch encoder system. Such model has good flexibility and interpretability. Moreover, we can specify different types of encoder and decoder based on testing scenarios. We further propose an alternate attribute tree, UAT, as a reference to design the optimal system architecture. This UAT is built based on acoustic knowledge. We first divide the training data into two groups, one from male and the other one from female. In this way, we have two nodes in the first layer. Then each node is further divided into two parts, one for high ASMR and the other one for low ASMR. Then the second layer has four nodes. Based on this UAT, we can then build DAEME system. From the experimental results, we first note that the ensemble learning approach, DAEME, outperforms original BLSTM. We also note that when there are more speech enhancement models, we can obtain better performance. Next, I'm going to present the objective function factor. Very often, I use this example to explain why we want to use different objective functions for speech enhancement. These are two Chinese oracles. Usually, we can tell the meaning of Chinese oracles by its shape. This one is an ear. This one is a mouse. For the left word, there's a man with a big ear carefully listening. For the right word, there are two mouses and only one ear. One ear is listening to two mouths speaking. The meaning of these two words are both hearing, but are not exactly the same. For this word, these are two mouses speaking into one ear, meaning just hear something and may not fully understand. For this word, a man carefully listening, meaning listen and understand. This word is 闻 in Chinese, and this word is 听 in Chinese. A famous book says, hear but pay no attention, listen but not hear. We can infer that intelligibility and quality are different. As mentioned earlier, conventional deep learning-based speech enhancement models are trained using either L1 norm or L2 norm, that is MSE. The reason is that these two distances are easy to compute and differentiable, thus can be easily used to update deep learning-based models. We argue that this is not perfect. For different tasks, we should design specific optimal objective functions. Based on this concept, we have been working on task-oriented objective function to replace the original L1 norm and L2 norm. For human to human, we should consider speech quality and intelligibility. For human to machine, we should consider ASR or word error rate. First, let us focus on human to human communication. We care about speech quality and intelligibility. The best way to evaluate the speech quality and the intelligibility is to conduct listening tests. That is to say, we play a speech sample and the listener gives a quality score and conducts a recognition test. Based on the result, we can know that the quality is 3.0 in a 5-point scale, and the recognition result is 0.8. That means 8 words can be correctly recognized out of 10 words. It is clear that for an accurate evaluation, we will need to prepare a lot of speech samples. However, it is not feasible to conduct human listening tests for a large amount of samples. Accordingly, we resorted to 2 evaluation metrics, PESQ and STOI. These 2 metrics are used to evaluate speech quality and the intelligibility, respectively. Many studies have confirmed that these 2 metrics are highly correlated to human perception. Therefore, when designing speech enhancement to improve the speech perception, we should consider these 2 metrics. Based on this concept, we have proposed several solutions. The first one is a direct optimization approach, and the second one is an indirect optimization approach. These 2 works were published in IEEE TASLP and ICML, respectively. This is the system of STOI computation. There are 2 inputs to the system. One is clean speech, and the other one is noisy or processed speech. The overall STOI computation has feature extraction, filtering processing, and correlation computation stages. We can finally obtain the STOI score. Again, this score has high correlations with speech intelligibility. Because all of these processings are linear, we can directly use the STOI as an objective function to train the model. Now, the goal of speech enhancement is to increase the speech intelligibility when transforming the noisy speech signals to enhanced ones. These figures show the results of human listening tests. Under 2 SNR conditions, we evaluate the intelligibility and the quality. The range of intelligibility is 0 to 100. The range of quality is 0 to 5. We are comparing 4 approaches: noisy, FCN with L2 known MSE, FCN with STOI, FCN with L2 known plus STOI. The FCN model is the same, but the objective functions are different. From the result, we can see that in terms of quality, the combination of MSE and STOI performs the best. Please see this one and this one. In terms of intelligibility, the combination of MSE and STOI also performs the best. Please see this and this. We also noted that with the same model, but with different objective functions, the evaluation results are rather different. In addition to STOI, we also investigated how to optimize the PESQ scores for the speech enhancement model. However, comparing to STOI, the PESQ computation is much more difficult. Because many parts are not differentiable, we cannot directly apply backpropagation to update model parameters. In addition, the PESQ computation is very complex. For the MATLAB code of PESQ, there are in total 2,700 lines. Previous studies have proposed to use reinforcement learning approach to optimize the model based on PESQ. Another study proposed a direction sampling way to optimize the model based on PESQ. Some other works proposed to approximate the PESQ score and make it differentiable. We proposed another solution based on quality net. The idea is actually quite simple. This is how we compute PESQ scores. The input to the PESQ computation are noisy or processed speech and clean speech as reference. The output is a PESQ score. We can train a neural network model which can predict PESQ scores. This network is termed quality net. Then, based on this quality net, we can optimize speech enhancement model by maximizing the output score of quality net. In this way, we can also train a speech enhancement model that aims to maximize the PESQ scores. As you can see, the overall system is very similar to a conditional gain-based system. Let us take a look at how conditional gain can be used to train the speech enhancement system. For traditional deep learning-based speech enhancement systems, the L1 norm or L2 norm MSE is used to update G, the enhancement model. For GAN-based speech enhancement system, instead of using an objective function to compute the difference of output and clean speech signals, we use a discriminator D to distinguish the output and clean speech signals. If D can easily discriminate the output and clean signals, meaning that the output is not good enough, and then D will force G to update model parameters. After parameters in G have been updated, G can then generate better output. Then D also has to become better to further discriminate the improved output and clean speech signals. In previous studies, directly using this conditional GAN structure could not effectively improve the STOI and PESQ scores. In 2019, we proposed a metric GAN approach, which was published in ICML 2019. The idea is to replace the original D from generating 0 and 1 to generating a specific metric score. More specifically, we propose to replace D with a judge here. When specifying a target metric score, either STOI or PESQ or other evaluation metrics, the discriminator will force G to generate the output that reaches the target score. When specifying a high metric score, D will force G to generate the output with high metric scores. On the other hand, when specifying a low metric score, D will also force G to generate the output with low metric score. Here are the comparison of conditional GAN and the proposed metric GAN. These two equations are used to update the discriminator. The goal of conditional GAN is to distinguish real and fake samples. The goal of metric GAN is to make the discriminator generate the same output as PESQ and STOI metrics. To train the generator, the conditional GAN aims to generate samples that can cheat the discriminator. On the other hand, the metric GAN generates the output that achieves the assigned score S here. From the result, we first note that the conditional GAN did not directly improve PESQ and the STOI scores as compared to L1 norm. Similar results have been reported in many papers. Next, we can see that if we use the metric GAN to optimize the PESQ scores, the metric GAN indeed achieves the highest PESQ scores. Meanwhile, when we use the metric GAN to optimize the STOI scores, the metric GAN indeed achieves the highest STOI scores. This confirms that the metric GAN can be used to optimize either metrics. We further investigate to assigning different target scores to metric GAN. On the top, these are noisy and clean spectrograms. For the clean speech, the STOI is 1.0 and the PESQ is 4.5. For the noisy speech, the STOI is 0.778 and the PESQ is 1.914. Using the STOI case as an example, when we specify the target STOI to be 1, we can have enhanced speech with improved STOI scores. Here we can have 0.808. On the other hand, when we specify a lower target score, for example, STOI to be 0.2, we can also obtain speech with STOI equals to 0.237. The same results can be seen from the PESQ parts. The conclusion here is we can specify a metric score to either increase or decrease the speech quality or intelligibility. A potential application will be we can determine the price based on the required quality or intelligibility for customers. Next, we intend to use speech recognition results as an objective function. However, there is a problem to directly use the recognition results as an objective function. That is because the ASR might be provided by a third party, for example, Google or Siri, and the ASR can be a completely black box to us. What we can get are the input and the recognition results. With such input and output information, we want to train a speech enhancement system that can pre-process the noisy speech signals before sending them into the ASR, the Google ASR or Siri. In 2018, we proposed a reinforcement learning system. This is a system which consists of 3 stages in the training phase. Number 1, IBM clustering. IBM is for ideal binary masking. Target, action determination, and action estimation. In the first stage, we first prepare the templates of IBMs. Each IBM template is an action in the proposed method. Because there are too many IBM templates, we run a k-means clustering to group these IBM templates into C groups. For example, if C equals to 10, then we have 10 IBM templates. Then we have 10 actions. In the second stage, given a noisy segment, we compute the ASR score for each action. The action that gives the highest recognition scores are kept as the true answer. In this example, number 2. In the third stage, the action is treated as target answer to the given segment. Then we can train the DNN model, where the input is the given segment and the output is the target action. During testing, given a noisy segment, the DNN model first generates the target action. Remember that the target action is an IBM template. Then we can use this IBM template to enhance the noisy speech segment. Finally, the enhanced results will be sent to ASR for recognition. In the top table, we report the results of noisy speech recognition. The numbers shows the word error rates. Lower word error rates mean better recognition results. From this table, we can see that the proposed reinforcement learning-based speech enhancement can provide better recognition results. In addition to ASR results, we also measure the PESQ and the STI scores of enhanced speech. The results are very interesting, as shown in the second table. Although the goal is to improve ASR performance, the enhanced speech also improve STI and PESQ scores. This plausibly suggests that the current ASR system and human perception are positively correlated. In addition to the above objective functions, there are numerous other works, at least some of them for your reference. Next, I'm going to introduce the auxiliary input. The idea of auxiliary input is, in addition to speech signals, we incorporate some complementary data into the speech enhancement system in order to achieve better speech enhancement performance. In this tutorial, I will cover 3 works. They use image, vibrations, and text as auxiliary inputs. The first auxiliary input is image. The model structures is like this. We have 2 inputs, one speech and another one is images of lip sequence. For the audio part, we use the clean as a reference. This part is the original audio-only speech enhancement system. For the visual part, we directly reconstruct the lip sequence. The idea is to provide additional and complementary information to perform speech enhancement using the reconstruction constraint of lip sequence. From our experimental results, we note that when visual information is provided, the speech enhancement model can achieve better PESQ and STI scores. We also test the recording in a night market environment. In this condition, the background is dark. However, the lip sequences are still okay. In this case, the proposed audiovisual speech enhancement system can still work reasonably well. The results suggest that the system is more robust against background, and the quality of lip sequence may not be critically important. Based on the above findings, we have proposed an improved version, which is accepted in Interspeech 2020. we call the new system as light AVSE. The main concept is, or main task is speech enhancement. But when implementing the system, the visual part is very big, actually much bigger than the audio part. In light AVSE, we decide to use an autoencoder to compress the image data. Then we can use the latent representations as the input to the AVSE system. In this way, we can reduce the image data size. To further reduce the data size, we apply another data quantization stage to compress the latent representations. This is how we extract the latent representation. We first crop the mouse region from the whole face. Then the mouse region will go through an autoencoder, and we only take the encoded latent codes to represent the original images. Then we can further quantize the latent representations by an EOFP procedure. This EOFP is a data compression technique. You may find more details from this paper. By this autoencoder and the data compression procedures, we can have two advantages. First, the data size can be considerably reduced. Second, the privacy of the speaker can be protected. More specifically, we cannot find the speaker identity from the quantized latent representations like this. From the results, we observe three consistent trends. First, audio-only speech enhancement gives higher scores in different SR conditions over unprocessed noisy speech. This is reasonable. Second, audio-visual speech enhancement outperforms audio-only speech enhancement across different SR conditions. This is also reasonable. Then we find that light AVSE slightly outperforms original audio-visual speech enhancement system. This is interesting. This might be owing to the latent representation has a more compact format. Some redundant information are removed. Finally, we know that if we further use the EOFP data compression on the latent representation, the performance starts to degrade. This might be owing to that the precision is reduced too much. However, at this time, the size of video part has been notably reduced 48 times. The second auxiliary input is bone-conducted speech. As mentioned earlier, while air-conducted speech is easy to be distorted by active noise, bone-conducted speech is robust against noise, but some losses in high-frequency regions, like this. By combining these two types of speech, we can restore clean speech more effectively. In this work, two ways of integrations are investigated: early fusion and late fusion. For the early fusion, bone and air-conducted speech are combined in the signal level. On the other hand, for the late fusion, bone and air-conducted speech are first processed by neural network models individually. Then a fusion network combines the outputs of these two models to generate the final enhanced speech. In this paper, we conduct enhancement in the time domain, and a fully convolutional network FCN was used as a speech enhancement model. Then the two fusion strategies are obtained: FCN EF and FCN LF for early fusion and late fusion, respectively. We test performance using PESQ, STOI, extended STOI, and listening tests. From the experimental result, we can first note that bone-conducted speech can improve the speech enhancement performance. As you can see, that these two multimodal systems outperform the audio-only systems. Next, we found that the late fusion outperforms early fusion. The next auxiliary input is text. In noisy conditions, if we know the speech content, we may more easily understand the speech. Therefore, we decide to combine text information to obtain better speech enhancement performance. In real-world scenarios, we will need an ASR. Usually, we will have a monophone ASR. However, in noisy conditions, monophone recognition may not be accurate, and thus may even misguide the speech enhancement process. Instead, we decide to use another approach, broad form class, BPC. We decide to use BPC information instead of monoform information. Here are two examples of recognition results. In the left side, it's a higher SNR condition, 10 dB. Both monophone and BPC recognition results are good. However, in the right side, lower SNR condition, 0 dB SNR here, monophone recognition results are very bad, but BPC recognition results are fine. This analysis motivates us to use BPC information to guide the speech enhancement process rather than monophone. We have investigated 3 BPC definitions. The first is based on place of articulation. The second is based on manner of articulation. And the third is the data-driven approach, meaning that we group monophones by their distance between each other. During training, we prepare a BPC recognizer. During testing, we use this BPC recognizer to obtain BPC posterograms. Then we use another autoencoder to compress these BPC posterograms. The compressed BPC posterograms are used as auxiliary input, which is combined with speech features as a final input to the speech enhancement model. From our experimental results, we first found that a transformer-based model can yield better performance than BLSTM in our task. Thus, in the following experiments, we used the transformer model as a core speech enhancement model. To verify the effectiveness of BPC posterograms, we designed a ground truth experiments. The clean testing data are processed by monophone recognizer and the BPC recognizer to generate the monophone and BPC posterograms. From this set of experiments, we confirmed that both monophone and BPC posterograms are helpful for speech enhancement, while BPC posterograms achieve better results than monophone posterograms. Next, we test a real scenario. The noisy testing speech are processed by monophone recognizer and BPC recognizer to generate the monophone and BPC posterograms. The result shows that the BPC posterograms can enable speech enhancement system to yield better results than monophone posterograms. There are many other types of auxiliary input. Here are list some of them for your reference. Next, I'm going to talk about model compression. Edge computing has become an important topic. We want to apply a speech enhancement system on edge devices for various applications. Model size reduction and computation efficiency are two important factors. There are several works proposed to deal with these two factors already. I will cover some of them, where speech enhancement is the target task. First, a aware-sharing technique can be used, which can be realized based on the K-means algorithm. The idea is we intend to group weights in the model into several clusters and only use the cluster centroids to represent the weights. This is example. We have a 4x4 filter. After performing weight sharing, we only use 4 clustering centroids, and we have a 4 cluster index number 0, 1, 2, 3. Assuming that originally each weight is represented by a 32-point floating point, and thus the total number of bits for the filter will be 16 times 32 bits. After weight sharing, we have 4 centroids. Each is represented by a 32-point floating point. So for this part, we need 4 times 32 bits. Next, we have 4 index numbers. So we will need 16 times 2 bits. Finally, the original 512 bits are reduced to 160 bits, more than 3 times. We apply the weight-sharing technique to speech enhancement. The parameters in the speech enhancement model are grouped into different number of clusters from 64 to 2 clusters. Original here means that the results of original speech enhancement model without performing weight sharing. The results show that the performance does not change much when the number of clusters are from 64 to 16. However, the performance drops significantly when the cluster number is less than 16. The results suggest that 16 clusters strike a good balance between performance and the model size. The second model compression approach is based on parameter pruning. The goal is to remove redundant weights in a CNN model. To implement the parameter pruning, we first define a sparsity score for each channel. Then we define a threshold to remove the channels that have higher sparsity scores than the threshold. In this paper, the parameter pruning approach was used to reduce the speech enhancement model size and online computation costs. In more details, there are 3 steps. For the first 2 steps, we try to compute a sparsity score for each channel. For the third step, we define a threshold. The channels with sparsity scores higher than the threshold are pruned. It is clear that if we use a lower threshold, more parameters will be pruned. These are the results of parameter pruning on the speech enhancement task. The results show that when the threshold is smaller than 0.7, the performance starts to drop notably for both quality and intelligibility. Please note that for the 0.7 case, the model parameters have been already reduced 20%. Finally, we try to combine the weight sharing and parameter pruning techniques. With a careful design, we can successfully reduce the model size to 10% without notable performance drops. Meanwhile, the computation cost is reduced 20%. The last factor I'm going to cover is model adaptation. As I have mentioned earlier, if there is a mismatch between training and testing condition, the speech enhancement performance may be degraded. A critical solution is to adapt the model based on a small amount of adaptation data to match the testing condition. This is called model adaptation. There are 2 different scenarios. If paired noisy and clean adaptation data for the new environment is available, we call this type of adaptation the supervised model adaptation. If paired noisy and clean adaptation data for the new environment is not available, we call it unsupervised model adaptation. Generally, supervised model adaptation is more effective than unsupervised model adaptation. However, it requires paired noisy and clean adaptation data. First, let us consider the supervised model adaptation scenario, where the paired noisy and clean speech data for the target domain is available. Using this figure as an example, if we only have ambulance noisy speech to train the speech enhancement model, then the performance of using this speech enhancement model to test on the data of the target domain, which may be a different type of noise or different speakers, the performance may not be good. If we adapt the model to the target domain, we can successfully improve the speech enhancement performance in the target domain. This is good. However, the direct adaptation may cause another problem, which is catastrophic forgetting issue. That is to say, the adaptive model has forgot the knowledge learned from the source domain. The speech enhancement performance is not good if we test the source domain speech using the adaptive model. To address this catastrophic forgetting issue, a serial approach has been proposed. This is how serial works. A direct adaptation will transform the speech enhancement model from the source to target domains, from here to here. We intend to incorporate some regularization terms into the model adaptation process so that adaptation is from here to here. Please note that this region is the overlapped region of source and target domain. The idea is to consider both new loss and old loss when adapting the model. The old loss is from the data in the source domain. The new loss is the data from the target domain. For model adaptation, the old loss is from the training data, which may not be available during adaptation. We need to use some techniques to formulate this term. There are two types of method. One is curvature strategy, and the other one is path optimization, and the serial use a combination of them. This table shows the result of serial. First, we note that the original model performs best on the original testing data. This is very reasonable that the original model without adaptation can perform well on the original testing data. Next, a direct adaptation suffers from catastrophic forgetting issue. Third, serial can improve the performance for the new testing condition while maintaining good performance on the previous conditions. Next, let us consider the unsupervised model adaptation scenario. We can use a game-based model adaptation approach. In Interspeech 2019, a noise adaptive domain adversarial training approach has been proposed. In this approach, we consider the speech enhancement system as an encoder-decoder architecture, E and G in this figure, respectively. Both encoder and decoder are trained to minimize the reconstruction errors. We use a large amount of training data to train the encoder and decoder. For unsupervised model adaptation, we want to adapt the model to the target domain without clean training data from the target domain. For the domain adversarial training approach, the noisy speech data for the source domain goes through two passes, E and G and E and D, and the noisy speech data for the target domain goes through only one pass, E and D, and there is a gradient reversal operation here. This classifier determines the noise types of the input speech. If you are familiar with GAN, you will know that the system is just a domain adversarial training-based model adaptation. Based on this setup, we can obtain noise type invariant code here, and the code is then going through G to reconstruct enhanced speech. This plot shows the experimental results. The lower bound, BLSTM-L, is the result without model adaptation. The number after BLSTM denotes the number of utterances used for model adaptation. From the results, we can first note that the proposed method can effectively improve the PSQ scores over lower bound. The results also show that when we have more adaptation data, the DAT can give higher PSQ scores. In addition to adapt noise types, we can also adapt speakers. In Interspeech 2019, we proposed a speaker-aware speech enhancement system. This is the overall system. We incorporate a speaker-embedded network here. The noisy speech goes through this network. The embedding vector is then integrated into the enhancement model. In this way, the speaker characteristics can be incorporated into the speech enhancement procedure. For all the noisy speech, we noted that the SADAE, the speaker adaptive DAE, achieves better performance than DDAE and noisy speech. We further compare the results of different noise types. The results also show that SADAE outperforms DDAE for both PSQ and STOI with a notable margin. The results suggest that the SADAE can be used to address the mismatch caused by the speaker factor. Next, I'm going to present how we can use speech enhancement for assistive voice communication technologies. Assistive voice communications can be divided into assistive listening and assistive speaking. In my team, we have been working on both parts. In this tutorial, I'm going to present one example for each part. For assistive listening technology, I'm going to introduce cochlear implant. For assistive speaking technology, I'm going to introduce disorder speech enhancement. This is a cochlear implant device. There are two parts. This part is a speech processor, which processes speech signals. This part is a transmitter coil, which sends power across the skin to the internal device by radio frequency transmission. This figure shows the complete cochlear implant system. The speech processor in the outside will transmit the signals into the receiver, which has been fixed on the skull. The electric signals are then passed to the electrode to stimulate the nerves. The fundamental theory of the electrode designs are based on the traveling wave theory. The cochlear implant has been widely used and considered as a very successful assistive listening device. In quiet conditions, speech understanding of cochlear implant users are very high. However, in noisy conditions, the performance of speech understanding decreases notably. Such phenomenon has been reported in this study published by Professor Chen. To handle this issue, deep learning-based speech enhancement can be a feasible solution. This is a block diagram of signal processing of a cochlear implant device. This is speech processor, this is transmitter, this is receiver, and this is electrodes. The acoustic signals are processed by bandpass filters, envelope detection, compression, and post-generation to generate the electric stimulations. To verify the effectiveness of speech enhancement for cochlear implant, we place the speech enhancement unit right after microphone. The listening tests were conducted by playing noisy speech to cochlear implant users. Generally, we will not directly test new algorithms on cochlear implant users. We first evaluate the signal level performance. This NCM is an object evaluation metric, which is often used to predict speech intelligibility for cochlear implant users. For the NCM scores, the higher the better. From the results, we can clearly see that the deep learning-based speech enhancement approach yields higher NCM results than traditional speech enhancement method. Next, we test performance using cochlear implant simulations. That is, we recruit normal hearing people to conduct listening tests on the simulated cochlear implant signals. This plot shows the listening test results. We test the performance under different SNR conditions, and the vertical axis stands for listening test results. The higher, the better. Percent correct shows how many words can be accurately recognized by all words. From the value, we can easily see that the deep learning-based speech enhancement gives the highest recognition results. Finally, we collaborated with a hospital, Zhenxing Hospital, to conduct listening tests. We recruited 9 cochlear implant users to conduct the listening tests. The results are shown in this figure. The vertical axis also shows the listening test results. Again, the higher, the better. From the results, we can see that the deep learning-based speech enhancement method significantly outperforms conventional speech enhancement method. If you want to know more, please refer to these papers. The second application I'm going to share is speech enhancement to improve the intelligibility of impaired speech. The target is individuals who receive oral cancer surgeries. These are the photos of individuals before and after receiving oral surgeries. It is clear that after oral surgeries, some muscles or nerves may be hurt, accordingly affect the pronunciation and generate speech with low intelligibility. Our goal is to convert the speech signals after surgeries to the enhanced one with improved speech intelligibility. Our first work is based on non-negative matrix factorization, NMF. The NMF approach is a dictionary learning method. We learn basis both before surgery and after surgery. During online, we want to transform the distorted speech to normal speech. This figure shows the learned basis based on NMF. The top one is after surgery. The bottom one is before surgery. Each basis can be considered as a particular phonetic unit. For example, this one only has low frequency components and should be a vowel sound. And this one has high frequency components and should be a consonant sound. We can see that the basis learned from before surgery are quite clear. However, the basis learned from after surgery are very noisy, especially in the middle frequency regions. We can easily tell that the speech intelligibility should be poor with the basis from after surgery. Here are some demos. Top ones are after surgery, bottom ones are processed by NMF. We can clearly see the speech structures become much more clear after enhancement. We also test STY scores. The results show that STY scores are increased after enhancement. If you want to know more, please refer to our paper. Later on, we propose a game-based solution. If you are interested in this work, please refer to this paper. Finally, I'll summarize this part of tutorial. In this part, we first introduce the architecture of deep learning-based speech enhancement. Then we present 6 factors that should be considered when building the speech enhancement systems. Next, I introduce 2 applications, one assistive listening device and the other one assistive speaking device. Both are benefited from the speech enhancement technologies. There are still several related works not covered in this tutorial. Here I list some of them, including unpaired speech enhancement, post-filtering, other modalities, meta-learning, mask-based speech enhancement. Due to the time limitation, they are not fully covered, but they are also important topics in speech enhancement. Here, I provide some useful links. Speech enhancement papers, useful codes, and data can be accessed from these links. We have made a mobile application based on the deep learning-based speech enhancement. This is a demo.
Hello.
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 I can't hear you.
Hello.
Oh, Stephen, it's more clear.
Hello.
Where are you? I can't hear you.
Hello.
Oh, I can hear you.
Hello.
Oh, Stephen, are you in the street?
You can see that The application now supports speech enhancement, model adaptation, and also acoustic scene conversion functions. It should be very useful, especially the acoustic scene conversion function. You can scan the QR codes to download the application. Please also give us your invaluable comments and suggestions, which will be highly appreciated. This is my team. Most of my works are done by this promising young man. I appreciate their help very much. Here are my contact and publication links. If you have any questions or anything for discussions, please feel free to contact me. Here are some references. This is the end for this part. Thank you very much for your attention.